So two sessions have happened. This is the third session.
Okay, sir. Okay, sir. Is this? I find the course session one in the YouTube. Two also available, na?
Yeah, two is also there.
Okay, sir. Thank you, sir.
Thank you. Okay, so let's start. So I welcome you all to week 3 live session of NPTEL Semiconductor Device Modeling and Simulation course. I'm Om Maheshwari, and today we will be discussing some questions that may help you with your assignments as well as your exams. So let's start. So in this week we'll be
Uh,
discussing about uh, yeah,
Sir, uh, one more time interrupt, sir.
yeah.
Actually, sir, I think those who are not attend the lecture week two, is
Hmm.
there any difficulties are there?
No, I don't think so. Have you watched the videos?
Yes, I watched the first video, but not second one.
No, no. I'm not talking about the live session. See, you need to watch the videos that are there in the NPTEL course.
I start from first week, sir. Actually, I'm late joining.
Okay, so what you can do is maybe just uh, I'll explain how I'll be solving all the questions. So the purpose of these live sessions is not to like teach you the entire course, but rather you will be learning the theory, most of the theory part from the NPTEL's video lectures by Professor Dixit. And
Okay,
later
sir.
every week, me and another TA will be taking two live sessions where we'll be solving some questions based on the theory being taught in those live session
Okay, sir.
in those
Okay.
lectures. So
Okay,
we'll
sir. Okay.
mainly be talking about some questions, but definitely we'll talk about like that little bit of theoretical background. But to get the full understanding, I recommend you watch the video lectures at the NPTEL website of the course.
Okay, sir. If sir today any topic I cannot understand, is that asking is possible, sir?
Yeah, yeah, sure. You can ask.
Okay, sir. Thank you, sir.
Okay. So we will be talking about mainly density of states, electron mobility, semiconductor statistics, Fermi-Dirac function, and carrier concentration calculation. So these are the week 3 topics. So let's start with the first question. So the first question is the dependence of drift velocity on electric field for n-type semiconductors shown below. So this is the dependence they have shown. N-type silicon with majority carrier of 10 to the power 13 per centimeter cube of concentration is biased with 1 volt across the length of semiconductor of 1 micrometer. Calculate the drift velocity. So do you know how to solve this?
No, sir.
Okay, so I'll help you solve this one. Okay, so we have been given we have 1 volt source of 1 volt across a length of semiconductor of 1 micrometer. So what is electric field? Field is V by L. Okay, voltage per unit length is electric field. So this will be 1 volt upon 1 micrometer, or say I write it in centimeter, 1 volt upon 1 into 10 to the power minus 4 centimeter, which is 10 to the power 4 volt per centimeter. This is the electric field in the semiconductor. Okay, so next thing is we have to calculate the drift velocity. So if we see this graph, so this graph is what? Drift velocity versus electric field. And you will learn more like why this graph looks like this. I will not go into the very depth of it, but let's just consider it mathematically for now. We see there is some linear dependence of drift velocity on electric field. So what I can write is Vd is proportional to electric field, right? Or Vd is equals to some constant. Let's call it maybe K E, right? So this is clear to you that Vd we can directly see is proportional directly with electric field.
Yes, sir. Yes, sir.
So this constant is nothing but mobility. Vd is actually equals to mu times E. That mu is the mobility, E is the electric field, Vd is your drift velocity. So this is a very well established relation in semiconductor theory. You can also read about that. Okay, so now next thing we know is Vd equals to mu times E. Okay, so we know E, right? We just found out. We have to find out what is Vd. For that, we need to know mu. And mu we can find from this graph, right? This mu will be nothing but the slope of this line. The slope will be
Sir, so
mu.
it is 10 to the power 7.
Vd, the value of Vd here is at this point is 10 to the power 7. The slope is not 10 to the power 7. We need to find the slope.
Slope is sir y by x, na?
Uh, yeah, that's true. So it will be 10 to the power 7 by 10 to the power 5. It is 10 to the power multiplied by 10 to the power 5.
Yes, sir. Yes.
Slope mu is 10 to the power 7 upon 10 to the power 5 is equals to 100 centimeter square per volt second. These are the units. Then match the units also is centimeter per second upon volt per centimeter. So it will be centimeter square per volt second. Now Vd we can find Vd equals to mu E, which is 100 into E is 10 to the power 4, which means Vd is 10 to the power 6 centimeter per second. So what options do we have? We have, okay, we do have 10 to the power 6 centimeter per second, which is the answer. Is this clear?
Yes, sir. Yes, sir.
Okay, good. So let's see the next question. Just read this question first.
Sir, here we have to find the J.
Yeah.
J is I by A,
All right.
and whatever for your previous problem, here mobility was given,
Hmm.
here length also given, so we have to find the area.
Okay. So we don't need to find the area. So if you know the current density J is mu times electric field. Okay. And this, okay, Q mu E. This is the current density J, which is nothing but NQ VD. VD equals to mu E. And for these exact specifications, 1 volt source 10 to the power 13 per centimeter cube
Yes, sir.
and 1 micro, we had already find VD is 100 centimeter per second. So we'll just substitute all the values. N is 10 to the power 13 per centimeter cube. Q will be let the electron charge 1.6 into 10 to the power minus 19, and VD is 100 centimeter per second. So if we do the calculation, okay, this was 100 into, sorry, 10 to the power 6 it was. Written 100, 10 to the power 6. VD was 10 to the power 6 centimeter per second.
So 1.6 is the answer, sir. 1.6.
Yeah, this is 1.6 ampere per centimeter. I think it is centimeter square. Yeah. So answer is option C. Is this question clear to all?
Yes, sir.
Yes, sir. Yes, sir. Yes, sir.
Okay. So the next question is calculate conductivity of a semiconductor doped with 10 to the power 16 per centimeter cube of pentavalent impurities. The mobilities mu n and mu p are given, and the intrinsic carrier concentration Ni is also given. So attempt this, then we'll solve it.
Option C, sir. 2.88.
Yeah. Okay, so let's see this one. So conductivity sigma is, yeah, C option is correct. Conductivity sigma is NQ mu. Or if we talk about both electrons and holes, let's say NQ mu n plus PQ mu p. This is the total conductivity of the semiconductor. Now we know that N will be equals to the pentavalent impurity, that means the donor, and D is 10 to the power 16 per centimeter cube. So P will be Ni square by N, which is 10 to the power 10 square by 10 to the power 16, which is 10 to the power 20 by 10 to the power 16 is 10 to the power 4, which is P. So this will be N is 10 to the power 16 into 1.6 into 10 to the power minus 19. Mu n is 1800 plus P is 10 to the power 4 into 1.6 into 10 to the power minus 19, and mu P is 1300. So this will be 1.6 into 1800 into all this will come out to be 2.88, and plus this will be 2.08 into 10 to the power minus 12. This term is very small, we can neglect this. So your answer will be
Option C, sir.
2.8 per ohm centimeter. Yeah, which is option C. Okay, so I hope everyone got this answer. Now
Yes, sir. Yes, sir.
let's move on to the next one. Calculate the intrinsic shift in the Fermi level when the semiconductor is doped with pentavalent impurity of doping Nd 10 to the power 15 per centimeter cube. Assume Kt is 26 milli electron volts, Ni is 10 to the power 10 per centimeter cube. Please attempt this.
Is point 026 na we are taking here.
Sorry,
KT we are taking like 0.026.
0.02. Yes,
Okay. Then 0.3 EV electron volt.
right. Did everyone get that answer?
No, sir.
Okay, so let's solve it. Just give me a minute. Okay, so we know that EF minus EI equals to KT by Q ln ND by NI. Okay, so if we just what we have to find is exactly EF minus EI only. Okay, so assume KT is 26 milli electron volt. This we have to replace here. 26 milli electron volts into ln, and D is 10 to the power 15, Ni is 10 to the power 10. 26 milli electron volt to ln 5. Sorry, ln 10 to the power 5. What is ln 10 to the power 5? Is 11.513. If you solve this, it will come out to be approximately 0.3 electron volt. Okay. 26 milli electron volt just means that into 10 to the power minus 3 electron volt. So 0.3 is the answer. So those who were not getting it, is there any issue? Do you want me to explain something in this?
No, sir.
Okay. All right. Mm, let's see the next one then. Okay.
A option, sir.
Yeah. A is correct.
Yes, sir.
Yeah. A is correct. Just a minute. The probability of finding an electron at Fermi level is 0.5. So if you remember, the Fermi function is 1 upon 1 plus e to the power e minus ef by KT. And if you plot it numerically, what you would get is Fe versus E if you plot. So Fe is nothing but probability of finding electron. Right? Probability of finding electron is F of E. So how Fermi function looks like is something like this. I have not drawn it properly. Okay. So at E equals to EF, its probability is 1 by 2. Here at 0 it is 1. So this is how the Fermi function looks like. Probability of finding an electron at Fermi level is half. Okay, so fine. Let's see the next one. Please read this one.
So is this D option?
Yeah, okay. So let's solve this one. So if you remember, Ni intrinsic carrier concentration can be defined as NCNV e to the power minus Eg by 2kT. Okay. So NCNV is nothing but density of states. It represents density of states, right? So since the question states that two materials A and B have identical band structure characteristics except for the band gap. So if the band structure characteristics are the same, that means their curvature and effective mass and everything is same, which means their NC, NV or density of states is same. So material A will have NC, NV, e to power minus, let's say, EGA by 2 kT, and material B will have NC, NV minus EGB by 2 kT. So what we have to do is just find the ratio of intrinsic concentration of material A to that of material B. So we have to find NiA by NiB, which will be this NC and NV will cancel, e to power minus EGA by 2 kT, EGB by 2 kT, e to the power, we take this at the top, EGB minus EGA by 2 kT, and EGB is 1.2 electron volts and EGA is 1 electron volt. This will be 1.2 minus 1 upon 2 kT is 26 milli electron volt. So generated at 26 into 10 to the power minus 3. Okay, so this will be e to the power, you can write as 0.2 into 10 to the power 3 upon 26 into 2 will be 52. So if I solve it, it will be e to the power 3.846, which is 46.812. So answer is option D. Is this clear to all?
Yes, sir.
Sir, kindly
Yeah.
tell me the band structure characteristics if the identical, then
Hmm.
effective mass and any other parameters, sir, which are constants, sir?
Uh, okay. So what they essentially mean here is, so actually, if we say this is a very hypothetical question, not practically possible. So what they're saying is there are two materials A and B. So band structure looks something like this, right? So this is material A. Material B has maybe something or more separated. So this is EG1, EG2. Now, when I say band structure characteristics other than this band gap, what I mean is mainly is related to the curvature of this, curvature or shape. So what they're saying is this entire shape is same, just that this EG is larger. And basically what curvature here will decide is your effective mass. And this effective mass will decide
Yes,
your
yes, sir.
density of states.
This is an EK diagram.
Yeah, this is EK. This is E,
Okay,
this is K.
okay, okay, sir.
So this is a very hypothetical case. It is not possible that we have entirely same uh, band structure except only EG is varying. So this is just a question for thought. But okay. Anything else in this question?
No, sir.
Okay. See the next one then. Please attempt this. So all of these questions you see are very basic questions, but all are formula-based simple questions. So you do need to know that those formulas, and these are important. So I recommend you learn them for your exams as well. They will not be given to you in the exam, so you do need to remember the all the relationships and the formulas between different quantities.
The answer is C, sir.
Uh, Let me check. Yes, it's C. Okay. So question is, given Boltzmann constant Kb, H, and the effective density of states conduction band at 300 Kelvin for not engineered semiconductor, you have to find effective mass of electron is given. So if you see the formulation for this, Nc, which is the effective density of states in conduction band, is 2 into 2 pi m kT by h square to the power 3 by 2, which is 2 into 2 pi ms 1.6 into, sorry, 9.1 10 to the power minus 31. K is 1.38 to the power minus 23. T will be 300 all divided by 6.626 10 to the power minus 34 square 3 by 2. So if you solve this, you will get 2.5 into 10 to the power 25 per meter cube, or in centimeter cube you will get 2.5 into 10 to the power 19 per centimeter cube. Okay, so you have to be mindful about units. So here all the quantities were given in the standard MKS system.
So it will be minus 3, sir.
Sorry, I could not hear you.
10 to the minus 3.
Oh, sorry, yeah, minus 3. Sorry. So please be mindful about units. Everything here is given in meter, kilogram, and second, but options are in per centimeter cube. So we need to do that conversion. Okay, so see you next one.
Sir, equal, sir. A, sir.
Okay. Yeah. So if you know EI is EC plus EV by 2 minus 3 by 4 kT ln ME upon MH. This is electron effective mass ME and hole effective mass MH. This is the relation. So if effective mass of electron and hole are equal, then this would become ln1, which is 0. Then your intrinsic Fermi level will lie in equidistant from conduction and valence, that is in between EC and EV, that is EC plus EV by 2. That will be the case when ln is 1, and that will be when ME equals to NH. So it's a simple question. Okay, so next one.
Sir, A.
Right. Okay. So option A is correct. So what actually happens in gallium arsenide is, so the conduction band looks something like this for it. Okay, so here this is the gamma point, and this is L point. So here you see curvature is like very steep. So here let's say m star gamma, and here it is m star L. So m star L is much greater than m star gamma. So what happens is when electron goes from this valley to this valley, the effective mass would increase a lot. So this would mean that on applying electric field, and if I plot velocity, the curve would become something like this. Okay, so if I see this is, let me call it mu1e, this is maybe mu2e. So basically its mobility is changing in both of the values, and in between this transition, when electric field is increasing, E is increasing but your velocity is decreasing, right? So this corresponds to a negative resistance. So GAS exhibits negative differential resistance because effective mass increases. So here we have higher effective mass m star L. Here we had m star gamma. So as effective mass increases, effective mass increases as electron shifts from central value to satellite value. This is the central value. It's going to some value on the side or the satellite value. So option A is the correct answer. Okay, see the next one.
Okay, sir.
Please attempt this question.
external bias or anything?
Yeah, option C is correct. Okay, so let's solve this. So what is given to us is we have a silicon sample doped n-type at 10 to the power 18 per centimeter cube of doping, resistance of 10 ohm. Sample has a cross-section area of 10 to the power minus 6 per centimeter square, the length of 10 micrometers. Determine the percentage of dopants participating in conduction. Mobility is given 800 centimeter square per volt second. Okay, so we know that resistance R equals to rho L by A. If I write it in terms of conductivity, R equals to 1 upon sigma L by A. Okay, so I can write that sigma equals to L by R A. If I substitute the values, all these are given. L is given as 10 micrometer, 10 into 10 to the power minus 4. If I converted everything in centimeter, R is 10 ohm and area is 10 to the power minus 6 centimeter square. So solve this, sigma will be 100 per ohm centimeter. Okay, so this is sigma, and we also know that sigma equals to nq mu. So here we know sigma, q we know is a constant, mobility also given. We have to find n. So n is sigma by q mu equals to 100 upon q is 1.6 into 10 to the power minus 19, and mu is 800. If we solve this, we get n is 7.815 into 10 to the power 17 per centimeter cube. Now we are giving the doping was 10 to the power 18 per centimeter cube. So Nd is 10 to the power 18 per centimeter cube. Now we need to determine the percentage of dopants participating in conduction. So we know these are the number of electrons that are conducting, and this is the total doping. So the percentage of dopants participating in conduction is just the ratio of these two. So percentage, the required percentage is n upon nd into 100, which is 7.815 into 10 to the power 17 upon 10 to the power 18 into 100. And we solve this, it is 78.15%, which is option C.
Okay, sir.
Okay, so let's solve a few more questions.
There is option C, sir.
Yeah, so if you've seen, I think, the density of states video, it's explained very well. So density of state in 1D is given as 2 upon pi h cross square under root m star upon 2 times of E minus EC. Density of states in 2D is m star upon pi h cross square, and density of states in 3D is star upon pi square h cross cube root 2 E minus EC. So 1D has 1 by root E dependence, 2D has no dependence on E, and 3D has root E dependence. So here they are saying is density of states is given by G C times some constant times e to the power n, and for 2D this n will be 0 as there is no dependence on E, which is option C.
Sir, 1 minute, sir. 1 minute. Okay, sir.
Okay. So next one, a current of 2 ampere passes through a wire cross section area 25 millimeter square. The number of free electrons in cubic meter are 2 into 10 to the power 28. The drift velocity of electrons is what?
Sir, this can be transformed in mobility into electric field, na?
Uh, you can, but mobility, you do not know the value of mobility, right? Try to use the uh, things given in the question to
Yes,
solve it.
yes, sir. Sir,
Yeah,
we can apply the formula, sir. The velocity equal to uh, current by NPA.
yeah. So current equals to NQVD. So this relation you can use. So first, but we have to find the this J is current per unit area.
Hmm.
So J we can find here, it is given 2 ampere per millimeter square. Oh, sorry, per 25 millimeter square. So if I convert it into centimeter, let's say centimeter square 225 into 10 to the power minus 2 centimeter square. So this would be 8 ampere per centimeter square. Now if I put it here, 8 ampere per centimeter square equals to, okay, N is given in cubic meters, right? So N is 2 into 10 to the power or uh, we can do one thing, we can find everything in meter, maybe that would be easier. Yeah. So if I find it in per meter square, it's J, maybe 10 to the power minus 6 meter square. Which will be 8 into 10 to the power 4 ampere per meter square. So we have to find VD. VD equals to J by NQ, 8 into 10 to the power 4 ampere per meter square upon N is 2 into 10 to the power 28 per meter cube. Q is 1.6 into 10 to the power minus 19 coulomb. So your
Sir, B is correct.
I have to see, I have not solved this one. Okay, so we have 8 upon 2 into 1.6, 10 to the power 4 on 10 to the power 28, 10 to the power minus 19. Okay, so can write this maybe 1, this is 0.2 to the power 1 will be 2.25 into 10 to the power minus 4 meter per second, I think. 25, 10 to the power minus 6 meter per second. What were you getting? B or C?
Sir, B is there, sir.
Okay, where have I made the mistake?
Sir, here 10 to the minus 4 is there, na?
Yeah.
Okay. 10 to the 4. No, sir, no, sir. Okay, okay, sir. 2.25, okay.
Okay, so anyways, I'm not like I don't know what the exact answer is, but basically you just have to use this and be mindful of the units. Okay, so you just have to
Okay,
do
sir. Okay.
some, just check the calculation again. For me, I'm getting option C, but check this. Okay, so to tell in terms of 10 to the power minus 6 meter per second. Okay, so see one more.
It would be D, sir.
Yeah. So question is the temperature dependence of resistivity of a sample of N-type silicon is based upon carrier concentration and carrier mobility variations with temperature. Because so you have to tell why resistivity, what all depends on temperature. Resistivity of silicon increases with temperature. This is false. Mobility decreases with temperature. This is true. Carrier concentration increases with temperature. This is also true. Resistivity of silicon decreases with temperature. This is true. So 2, 3, and 4 are correct, which is option B.
Yes, sir. Yes, sir. Okay, sir.
Okay, let's try one more question. Please attempt this.
sir, please solve the problem, sir.
Yeah, just a minute. Okay, fine. So we have been given that EF is 5.5 electron volt, and it is given that we have to find the temperature at which the probability, there is a probability of 2% that a state 0.25 electron volt below Fermi level is empty. Okay, so probability that the state is empty. So probability of finding an electron is Fe. So probability of a state being empty will be then 1 minus Fe. It is given that 1 minus Fe is 2%, which is 0.02. So 1 minus Fe is 0.02, then Fe will be 0.98. Okay, so we know Fe equals to 1 upon 1 plus e to the power e minus ef by kt. So if I just substitute the values, let's say if I take the inverse, 1 plus e to the power e minus ef by kt is 1 by Fe, or e to the power e minus ef by kt is 1 by Fe minus 1, or e to the power e minus ef by kt ln 1 by Fe minus 1. Okay, so Fe we know is 0.98. Let's just substitute the values. This E minus EF we also know that, right? So this is 0.25 electron volt below the Fermi level. So E minus EF will be minus 0.25 eV, right? This is 0.25 electron volts below the Fermi level. So this will be minus 0.25 by kT is ln 1 by Fe 0.98 minus 1. To solve this, it will again be ln 1.02 minus 1, which is ln 1 0.0204, something like that, which is minus 3.892. This is minus 0.25 by kT. So we have to find kT. Okay, so kT will be 0.25 upon 3.892, which is 0.0642 and T will be, so T will be 0.0642 upon K is given 8.61733. 61733 into 10 to the power minus 5 electron volt per Kelvin. And if you solve this, it comes out to be 745.2 Kelvin. Is this clear?
Yes, sir. Yes, sir.
So the only thing to like pay attention here is this. We have to take this 1 minus F is 0.28. That means F is 0.98.
Yes, sir. Yes.
And you have to take E minus EV as negative. These are the only two important points. The rest it's just uh, calculation. Okay, so let's stop here.
Okay,
If
sir.
so, I think these four questions were also from your current assignment. If you uh, so I also don't have their solution. I just solved them on my own. So, but do check the calculations before doing them in your assignment. And if you have any other doubts, you can email me, and I'll upload the recording as well as these slides on the in that sheet.
Sir, please provide the email, sir. Actually, this is my first class.
Email is on the first slide I had shown. om.maheshwari at iitgn.ac.in.
Okay, okay. Okay, sir. Okay. Thank you, sir.
Okay. Thank you
Sir,
for joining.
sir, is
Yeah.
there, yeah, after the recording is complete, sir? Is your recording is over?
Yeah, yeah. Recording. I'll just upload the recording and
No, no, you can stop the recording, sir. Yes.